welcome everyone and happy Jewish New Year today. We just had an excellent ITC colloquium by Emily Rauscher, who should be over there. And she will tell us some more about something else in a few minutes. We'll start with oh, I see. So the order was changed. Okay. Guido Risaliti from Arcetri will speak about X-ray spectroscopy of AGNs. Can we really measure black hole spins? And then we'll continue with Manasvi Lingam from the ITC that will talk about impact and mitigation strategy for future solar flares. I should mention that Manasvi is this year an ITC fellow, so he is one of our latest. Okay, that's a different order than I was given by Anastasia. Yeah. But, okay, so well, there seem to be two orders that were given, but at any event, following Manasvi, we'll hear from Emily Rauscher that will tell us about creating the perfect map of an exoplanet, and we'll finish with Hsin-Yu Chen from the BHI on advanced LIGO-Virgo observing scenarios and localization. Now, this is observing scenarios, it's not observational results, which I already know about. So pay attention to what she describes as scenarios, because she will probably not waste our time on scenarios that are not realized in nature. Guido, please, go ahead.
Okay. Thank you for inviting me here. And, okay, can you hear me? Yeah. So I will report about an ongoing exercise based on simulation of X-ray spectra of AGN with the goal of understanding whether we can really measure reliably black hole spins. Okay, this is a hot subject, and there is some kind of disagreement in the X-ray community about the capability of current instruments to put constraints on black hole spins, and so we thought that an extensive simulation program could help to solve this issue. So just a few seconds to review why spin measurements of, in particular, supermassive black holes are important. Okay, they carry a lot of information which is relevant for different fields in X-ray galactic astrophysics. First of all, the amount of spin is related to the amount of luminosity that can be emitted by a black hole for a given mass. And so the total radiative efficiency depends on the black hole spin. The black hole spin is obviously giving us information about the general relativistic effects around the black hole, and so it's in itself a fundamental physical check of GR. And then the spin of a supermassive black hole is a record of the accretion history of the black hole itself. And so it carries information of the formation history of supermassive black holes. And it's also relevant for the feedback, so for the impact of the AGN luminosity on the host galaxy, especially because it's related on the power of the outflows. So if we just look at this review, which is less than 1 year old, about current spin measurements. These are all nearby AGN, which are bright enough to do a detailed spectral analysis. Okay, these are the results. You see that the error bars are big, but I mean, we can say something about this distribution. There is a clear tendency towards high spin values. Okay, so one basic question is it real? Okay, is there a bias? Because higher spins are easier to measure because they are the ones which give the bigger changes in the spectral features of an AGN. So, these are open questions. So how do we measure black hole spins? Okay, basically the idea, based on X-ray spectroscopy, there are also other methods, but the idea is that we consider that the X-ray emission comes from a very small region, which we call the corona, made of hot electrons, which it is small, but it's not a point source, but in all our model, we approximate it as a point source, okay? And this is an important point in the sense that everything we do, which is not very realistic, goes in the direction of making things simpler, not more complicated. And this is a relevant point for the conclusion. I'll go back to this point at the end. So basically, this X-ray corona emits a primary emission, which is more or less a power law in shape. And of course, part of this emission illuminates the disk. And so we have a Compton reflection by the accretion disk. And this Compton reflection happens, at least in part, in the very inner parts of the accretion disk. And so we have that the reflected emission is affected by general relativistic effects. And so we try to use these effects, especially in general relativistic effects, so relativistic meaning and also gravitational redshift from the accretion disk, which is illuminated by this point source, these are just simple models to explain how a monochromatic emission, a line emission in the rest frame in the accretion disk is seen with a complex and asymmetric shape in the observed spectrum. And this shape depends on the several things, and it depends on the black hole spin. In all these models, we always assume that the disk extends down to the ISCO, so the last stable orbit, which has a different distance from the black hole in terms of gravitational radii depending on the spin, as you all know. And so basically, depending on the spin, we expect a different shape of these asymmetric lines. And in practice, this method is applied to the iron K alpha line, which is emitted in rest frame at 6.4 keV, because it's by far the brightest line. It's the only one where we can hope to to do this kind of measurement. So this is a business which is going on now for 30 years or so, and so there were expectations that with better and better instruments we could get better and better constraints for the black hole spin. And well, actually this happened, but not so much. Why? Because with better observations, we also learned that there is much more complexity than we expected in the X-ray spectrum of an AGN, and it is far from the intrinsic power law plus the relativistic reflection component. It's a mess, and this mess is mainly due by the interaction with the circumnuclear medium, which can be made by several components with different ionization states, and so we have multiple emission and absorption components which can mix up everything, and it's very hard to disentangle the individual components. So this is just an example of one source which was once considered the best one to measure black hole spins, because the relativistic line was very clear, and the more we observe it, the more, well, the relativistic line is probably still there, but the power law has disappeared. So we do not know, where to put the continuum, given this complexity, or at least it's very complicated. And so depending on how we fit the other components, we have a different measurement of the black hole spin, which depends critically on the shape of this red tail of the line. So what we did, we are three friends, myself and Elias Camus, who is a PhD student at CISA in Trieste, who is leading this work, and Emanuele Nardini, who has been a postdoc here, so some of you may remember him. And so we decided to do simulations this way. So each of us uses the best approximation of a real model. I will show you how in a second. Okay, to simulate the spectrum of a very bright AGN observed with the best observatories that we have now. So we simulate the best possible conditions for an observation. Okay, and we do it several times with different choices of the spectral parameters, and in particular with different choices of the black hole spin. Then, for each simulation, the other two do a blind fit without knowing anything, and then we compare the results at the end. So that should be, you can trust us with being fair. I mean, we didn't cheat. And so, and also because the results are a disaster, as I will show you in a second. So, okay, if we cheated, it was because we wanted to prove something wrong. So anyway, the model, this is the important point. It's a complex multi-component model, but it is not arbitrary. This is a very complex slide showing several components, but the bottom line is that this model comes from an observed source. This is not something that we decided based on a general analysis. Okay, there is, in particular, this source is NGC 1365, which is one of the more complex AGN in X-rays, but however, it's maybe the one with the most reliable spin measurement. Because this source is highly variable, and in particular, the reflection components are variable. And so disentangling the different spectral states make it possible to isolate the absorption components and so to do a reliable measurement of the spin. So this is a lucky case where variability helps us to see one by one the different components. Okay? So our model consists of two warm absorbers, two ionized absorbers with two different ionization states, and one neutral absorber plus the relativistic reflection, which is exactly what is observed. And this is not only in this source. There are other, basically the ones which are observed in detail and which are bright enough for a detailed spectral analysis show this kind of complexity. So this model is it's not too complicated. It's exactly what we see, and so what we should assume that we should use to do this kind of analysis on real sources. So on the left here, you see an example of one of our simulations. We more or less we assume to observe these sources for one orbit of XMM Newton, which is around 100 kiloseconds, and also simultaneously with the New Star Observatory, okay, which is the configuration which gives the highest sensitivity today for bright sources. And as I said, the intrinsic flux of these sources are taken a few milligrams, which is again corresponds to the highest fluxes. Okay, yeah, I just 2 seconds, I show the conclusion. It's the last slide. So for each simulation, we did a complete spectral analysis very carefully, as we would do for real data. And these are the results. Basically, we failed. We failed almost completely. Okay. So basically, the spin values used for the simulations are not recovered in general. There are cases where we simply have no constraint on the spin. In other cases, we find a different value of the spin. In all cases, we have a statistically acceptable fit. Okay, we consider a fit acceptable if it is as good as the one with the model used for the simulation. With the typical reduced chi-square is 1 here. And basically, we failed almost always. The only case where there is an acceptable result, not a complete success, but a reasonable success, is when we have a very high spin and the X-ray source is very close to the event horizon. So the configuration when we have the highest effect of the black hole spin, of the general relativistic effects. In all the other cases, we have a complete failure. So the conclusion is that maybe, more or less, we can measure very high spins for sources which are very close to the event horizon. In all the other cases, we cannot yet measure the spin through X-ray spectroscopy only. Thank you very much. Okay, sorry. I thought I was late, and so I'll put it back. Sorry.
Let me start by asking you, so some of the complexity will be associated with the beamer, the illuminator, the geometry of the X-ray emission above the disk, because that can complicate matters.
Absolutely.
So do we have any information about that? Because in principle, it could be reconnection events that occur in various places at different times.
Yes, so there is a lot of of activity on this, and okay, for this kind of measurements, they only make things more difficult because, of course, if you consider this complexity, you should add more degrees of freedom, and the degeneracy would even increase. Well, there are several models which are already complete, where at least, I mean, they are not dealing with all the complexities you are mentioning, but at least they try to have a self-consistent emission, considering that the ionization state of the disk depends on the illumination from the X-ray source itself. And they are only trying to make it not a point source, but extended. In my opinion, the main limitation of this kind of models is that anyway, we do not know the density profile of the disk. And so, depending on the density profile, you can reproduce everything. So it's these models are self-consistent, but adding one fundamental parameter, which is the density profile. And then, I mean, I don't think we will, maybe with the next generation X-ray telescopes, we will have more complicated models and constraints from the observation. But for now, yeah.
Well, that was a really brave presentation. Because, it's rare for somebody to come in and just honestly present results where they say very strongly that it didn't work out the way they wanted. So I made a suggestion, and I'm sure you've thought about this for a long time, but in terms of your feeling about the prospects long term, do you think that it is going to be possible to do this with spectroscopy? And if so, what would be the specific steps that you would take?
Yeah. Okay. So I think that the realistic and optimistic view at the same time, if you want to be optimistic but also realistic, we have to think that the next step should be trying to say if the spin is higher than 0.9 or lower than 0.9. Lower than 0.9 if it's 0.8 or 0.1, or that's very, 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 very difficult. Okay. Anyway, in the long term, I mean, doing these simulations, my expectation is that increasing the sensitivity will not help much. If I try to do the same kind of analysis with the Athena sensitivity, I get the same results. But what will help a lot will be the spectral resolution. So the calorimeter resolution, that will help a lot to remove many of these degeneracies. And also, which is what they are already doing today, using variability as a complementary tool together with spectroscopy. So adding all these things together, we may at least tell whether the spin is close to the maximum value or not. That's my expectation. Thank you. On a completely different subject.
Yeah. Hi. I'm going to speak to you about the impact and certain properties. Just a second. Yeah, I'm going to speak about the impact and mitigation strategy for future solar flare This is work done with Professor Loeb here at the ITC. And so let me just begin with a brief introduction of some of the properties of solar flares. So solar flares are explosive phenomena, and they're associated with the fast release of about 10 to the power 28 to 10 to the power 32 ergs of energy in about a span of 10,000 to 10,000 seconds. And the rapid energy release that occurs through flares is typically facilitated by a process known as magnetic reconnection. And most large flares are sort of accompanied by the emanation of high energy particles, which are sort of called solar energetic particles, SEPs for short, and coronal mass ejections, which are sort of large blobs of plasma that are flung outward. So they are called CMEs. And as I'll discuss later, trying to understand these phenomena is pretty important from the standpoint of human technology. And in it, so as I said, these flares are typically associated with energies less than or similar to 10 to the power 32, 33 ergs. But in addition, there's also a different class of flares known as super flares, which are greater than 10 to the power 33 ergs. And they've been documented to occur on a wide range of stars. For example, the Kepler mission in particular has revealed quite a lot about them. So before I get to the risk posed by flares, I'm going to talk briefly about the biological risk posed by superflares. And this is a work that was done with Professor Loeb, which is currently in press. And it turns out, as I mentioned before, that you have these sort of energetic particles that are emanated with, along with these superflares. And it turns out that they can react with the atmosphere of the planets, and they can basically react with the ozone in the planets and form nitrogen oxides. And this leads to ozone depletion. And of course, as you all know, perhaps from anthropogenic causes, that an ozone hole would lead to ultraviolet radiation streaming in and causing a lot of biological damage. So what we sort of estimate is that Earth-like planets at around 1 AU, around G-type stars, may be subject to complete ozone depletion, and as a result of that, there would be a series of harmful effects, and this could culminate in large-scale biological extinction, and this could occur for superflares greater than 10 to the power 36 ergs. Now, one might ask, what is the frequency of such events, of flares with around 10 to the power 36 ergs? As per the available data, which of course has lots of uncertainties, the associated time scale turns out to be on the order of tens of millions of years. And interestingly, this value is pretty close to a periodicity in the fossil extinction record on Earth that has been found to occur with a period of 26 million years. So this means that we sort of see a spike in the extinctions once every 26 million years or so. So it sort of looks like, so it's sort of tempting to think that superflares may play a role, even on Earth, in perhaps triggering mass extinction. But I should note that it still remains unknown whether superflares can occur on the Earth, and if they do, what their frequency is, and what the power loss is, and so on. And so this, of course, most of my discussion has been centered on G-type stars, but we also sort of consider K and M dwarfs briefly, and we sort of are led to believe that the damage caused by superflares, the biological impact, would actually be more for K and M dwarfs. Now I'll sort of get to the next part, which is the technological damage. And yeah, right, okay. And yeah, so I'm sort of going to talk about the technological risk posed by flares, and these are normal flares, not superflares. And so this was just posted on arXiv a couple of days back. And as I mentioned, human technology is very vulnerable to these events, solar energetic particles and coronal mass ejection. And collectively, they are called space weather events. And it turns out that the total worldwide economic losses that would result if a large flare and its accompanying space weather phenomena, if they were to hit the Earth right now, it would be around 10 trillion US. So just to give a comparison, this is about 1/7 of the world's GDP and about half that of the US GDP, and about 10 times more than the US defense budget. So this is for a Carrington type flare, so this is a large flare that occurred in 1859. And if a similar flare were to occur now, we are talking about damage that would be 10 trillion US dollars. And just to offer another comparison, this would be the equivalent of decades of damage caused by climate change. And the main damage would be due to damage to power grids, damage to satellites, and therefore damage to communications, and also damage to global supply chains. And so therefore it is necessary to quantify, to sort of try and understand how this economic damage scales with time, and therefore to also identify strategies by which we can at least mitigate some of the risk posed by these flares. So for the first part, in order to assess the economic damage as a function of the wait time associated with a flare, we sort of present a simple mathematical model and solve it. And the model, the graph, the plot is presented here. So you can see in the left-hand panel, there is a period of power law growth, and that sort of arises from the fact that if you wait for a longer period of time, you're going to have a larger flare, and a larger flare will cause more damage. And after that, you sort of see that the curve steepens, and that's where there's exponential amplification coming in. And this comes in from the fact that human technology has exponential growth. So that's where the exponential part kicks in at a slightly later stage. It turns out that the exponential stage kicks in at around 70 years henceforth. And then you can see that it saturates because, of course, economic growth, technological growth, you don't expect it to be ad infinitum. And so it sort of goes and then it saturates. So you can see the saturation there. So on the x-axis, we've plotted the economic damage in terms of the current US GDP, which is around $20 trillion. And what you have that was on the y-axis. On the x-axis, you have the wait time in years. And the value which you see, which is gamma m, that's sort of the maximum cap at which we sort of expect technological growth to saturate. So you can see that the saturation is obviously a function of the cap. So if you remove the cap, you will just have exponential amplification ad infinitum. And so here you can sort of see, this is in the linear scale, and it sort of just shows the early part. So there's the power law, and then there's the exponential part. And so we can see that there's a period initially where it's a power law, but after that it's beginning to amplify exponentially. And this happens at around 100 years or a little less than that. So it's therefore necessary to identify a potential strategy by which we could perhaps mitigate some of the damage caused by this flare. So we sort of propose maybe using a magnetic deflector, and we sort of use a deflector here, and it's situated at the Lagrange point L1, and it's between the sun and the earth, and the hope is to deflect charged particles that would be emanated during the solar flare event, and to sort of deflect them away from the earth. This is just a schematic figure. And then we sort of looked at some of the basic numbers, and we find that the deflection needed would be greater than 25 microgauss, and that the total mass of the structure is pretty heavy. It's around 10 to the power 5 tons. So it does sound very high, but it's about 1/10 the mass of the Great Pyramid of Giza, just as a comparison. And the power dissipated by ohmic heating, so we sort of envision the structure as a big current loop. And if you have a wire, you know that there's going to be a resistance and power will be dissipated. We find that the power dissipated by ohmic heating, it's not sufficient to melt the wire material, which is a good thing. And we also calculate the material strain imposed by the charged particles on the wire and find that it is negligible. And it turns out that the total cost to lift the structure into space, it's a 10 to the power 5 ton structure after all, a big one. And it turns out to be on the order of $100 billion US, which is about the same as the International Space Station and about 0.1 to 1% of the current world GDP. And to sort of conclude, so as I've said earlier, other stars may also be subject to flares and even super flares. So it's quite possible that if advanced civilizations do exist, they would want to come up with strategies to sort of mitigate the damage caused by these flares. And so we sort of identify a few techno-signatures which might be associated with such superflares. And to conclude, as I mentioned, the total damage that we are looking at these events is about, you can see that it's sort of dotted line is where the damage already reaches that of the current US GDP, which is $20 trillion. And you can see that it's sort of happening about a century from now. So it's absolutely necessary to sort of try and identify strategies by which we can mitigate the damage caused by these phenomena within the next century. Thank you. Oh, yeah. Right.
Asteroids could have killed the dinosaurs, could have caused damage that we identified in the past, but this damage was never identified because we didn't have the technology. Nobody cared about it.
Right. Yeah, that's a good point. The damage caused by asteroids has been recognized, and indeed you see it pop up. You know, NASA has this thing called the Pan-STARRS mission. You see it in science fiction movies. We know the dinosaurs died mostly because of an asteroid impact. But yeah, it's true that the resulting coverage for space weather is certainly, I think, a little lesser, much lesser than what it ought to be. Yeah.
Questions from us?
Yeah.
So I'm surprised by your magnetic field, only 25 microgauss, is that what you said?
Yeah, it's sort of.
What were you assuming for particle spectra in these flares? There must be moderately high energy particles, which will need a lot less.
Right, so that's true. So we sort of just took the sort of the value for a characteristic particle.
What energy?
It's around the GeV, the proton. It's a proton with an energy of around 1 GeV. And in fact, recently there was, there have been a series of big flares, and there's a spacecraft around Mars called MAVEN, which some of you might have heard of, and it has detected GeV protons. And we don't typically expect something much higher, like it's a power law again, and although there are some particles with 10 GeV and higher, it does turn out that the fraction is relatively low, so we sort of just took a sort of characteristic value of 1 GeV.
Super flare, I would think.
Oh yeah, of course, a super flare would be,
Much higher energy.
yes, definitely.
Is probably too conservative.
Definitely. I think so. But we sort of considered mostly flares because there's been a bit of controversy in the literature whether super flares can occur on the sun or not. And even when people do agree they can occur, the time scales vary between thousands of years to hundreds of thousands of years. So there's still a lot of uncertainty. Yeah.
So, so you're talking here about kind of this space weather event, right? So particles coming in, very high energy particles. But what about the radiation?
The radiation is also, it's a good point, but at least from the viewpoint of technology, we don't really expect it to have any damage on the surface because you have the ozone layer which protects most of the UV radiation and so on. And yeah.
But going back then to what you said at the beginning, so of course, we're talking here about the losses and the money.
Right.
But for us, it's more important to preserve the atmosphere, right?
Yeah, of course. There's certainly, this work is certainly not meant to be all-encompassing. Yeah, there is certainly an associated with risk associated with damage to the atmosphere as well. But I think based on what we looked at, the damage for flares, so there's this flare known as the Carrington flare, which occurred in 1859. And as of now, it still remains the biggest on record. And what people have found by doing simulations is that the ozone depletion is not too high. It's around 10% or so, and it can also repair itself in a fairly short span of time. Yeah.
Based on the reaction of Washington climate change, one would not be optimistic that there will be any action until the first few flares goes trillions of dollars in damage. But after that,
Right.
people will read this paper.
Yeah.
Thank you very much, Manasvi.
All right, thank you. Thank you.
Okay, so now for something completely different. This is still a work in progress, so you're welcome to ask me details about any plots I put up, but my answer might be, oh, I don't know, wait until we finish. Just be forewarned. But the idea, I think, is really fun, and I wanted to share it with you. So, basically, we can map exoplanets. We can get two-dimensional information, or three-dimension if we add wavelength. But let's start with two-dimension of what the planet actually looks like. And we can do this in a few different ways. Some ways not quite yet. But we can do spin to figure out what a planet looks like. And for hot Jupiters, sometimes we think of spin and orbit as the same because we assume they're tidally synchronized. And so as they go through their orbit, different regions rotate into view. And you can use that to construct a longitudinal map. We can also do eclipse mapping when the planet goes behind the star and different regions come in or out of view. The flux changes associated with how bright that slice was. And this is a nice little cartoon from a recent review chapter that was posted on the archive, and it's great, but it's actually a little more complicated than a cartoon. But it has been done successfully. This was the first example from your own Heather Knudsen, showing that the change in flux as a function of time, as a hot Jupiter went through its orbit, can be translated to brightness as a function of longitude on the planet. And, in fact, eclipse mapping has also been done too for a single hot Jupiter. Two different independent analyses use some stacked secondary eclipse curves for a particularly bright hot Jupiter to recover a 2D map. They paired this with a phase curve to get the backside as well. A map of the planet. But we're on the brink of being able to do this for plenty of planets, not just the single best example, once JWST launches. So let's think about a little bit more carefully how this is actually going to work and some of the dangers involved. Going back to this nice review chapter, we can think a little bit schematically about how different brightness maps correspond to the shape of the ingress and egress light curve. So, if all of the light of your planet was just at a single point at the center, then your light curves would be this black dashed line. You'd see the planet, and then instantly it would be behind the star and you'd see nothing, right? So on the top, if you could compare the black curve to the bluish teal whatever curve, you can see that the tilt of the ingress and egress is telling you something about the central concentration of brightness compared to more uniformity. Similarly, if you take a bright point and you shift it east-west, then that's going to shift the ingress and egress curves back or forth in time. And so that's kind of the expression of east-west information. And north-south information is going to shift the ingress and egress times, but in opposite directions. Now the problem is that these patterns may look familiar to some people here who do lots of transits all the time, because these similar patterns can also be reproduced by other physics. So for example, we've known since Williams et al. That eccentricity, for example, would be one of these things that shifts east-west. If you aren't sure about your eccentricity, then your planet could seem to be a little bit delayed in its orbit. And your north-south information is going to be degenerate with your impact parameter. How far are you from the equator? If you're a little bit farther down, then the length of your eclipse is going to be a little bit shorter. So this actually was all sort of nicely demonstrated in the paper by DeWitt et al., 2012, where they explicitly went through these different concerns. And they pointed out very clearly that there's this degeneracy between your map solution and your orbital parameters. And as much as I would like to think we know orbital parameters perfectly, unfortunately we don't, right? There's always an error bar. And so in this example, it's hard to see, but there's something like eccentricity there and something like stellar density here, which changes exactly the orbit you're on. Anyway, orbital parameters. And this kind of dotted constraint is what your preferred solution if you swim a uniform planet disk. And then the different colored curves are your preferred solution for those orbital parameters if you let your disk be non-uniform. So it's a trade-off between what's going on with the map and what's going on with the orbit. And a little bit worse than that, in order to retrieve this map, they tried different brightness models to fit to the data. And what you get in terms of a preferred solution depends both on your brightness models and on those orbital parameters, and different brightness models are going to skew your orbital parameters in different ways. Which sort of makes a little bit of intuitive sense once you start playing with this, right? You're trading off between different parameters. So how you choose to force those is going to trade off in different ways. Okay, so how can we actually know that this is a better map than this, or vice versa, or what actually should we be using for our maps? Well, I think mathematically we can figure this out perfectly. So this is work that an undergrad at Michigan contributed to. Poor soul, we didn't realize how complicated it would get when we assigned an undergrad to this project. But the basic idea is, let's start with spherical harmonics, which are a natural set of map components to use to describe a sphere. And we're going to take these spherical harmonics, and we recently updated our analysis to use Laura and Tom's Spider-Man routine, because it's so convenient. We can integrate these spherical harmonics. Let's choose this one, for example, and you're going to get a phase curve out of that. And there's a secondary eclipse in the middle. Don't worry about the fact that the units don't make complete sense and things seem flipped over. We're just doing mathematics for the moment. And this would be very simple, going from maps to just phase curves, but the secondary eclipse means that this region, I've zoomed in on secondary eclipse, this region of ingress and egress imparts information about the space, right? Okay, so we create a whole set of spherical harmonic curves corresponding to the maps, because it's the curves you're actually measuring, and we feed those through a principal component analysis. And this lets us identify both eigencurves, ones that are orthonormal to each other, which is useful for trying to reconstruct a non-degenerate solution, and we learn kind of how many pieces of information, no label on the axes. This is, I think, explained variance versus number of components. Basically, you have information, depending on the level to which you can measure it, from about 4 components, let's say. And so each of these eigencomponents has an associated, is an eigencurve, we might call it. And you can see, again, they look sort of like your harmonic curves, but now mathematically they're a better basis set. And each of these maps, because these are all linear combinations of the harmonic curves, mathematically this also means that each of these has an associated map where you just take those coefficients and distribute them among the spherical harmonics. And so you get a set of eigenmaps that are the perfect maps to use to try to map the data. Okay, so we can do this. We can take our eigencurves and we can fit them to the data. These are the actual data for that hot order that's been mapped. And then use the coefficients assigned to each component and multiply them and add the eigenmaps, and you get a solution. But I just glossed over the danger that I warned you about at the beginning, which is that different orbits will lead to a different translation at this point between your spherical harmonics and your harmonic curves. But that's fine. Actually, this setup already lets us accommodate that. So again, Spider-Man to the rescue. No, not a single chuckle. So we can do this. We can just, instead of calculating one set of harmonic curves, we can just change those orbital parameters, maybe sample a distribution of errors, and calculate a huge set of curves, do a huge PCA analysis, and at the end of the day, those different components are then going to not just tell us how to weight different eigen maps, but also tell us in a consistent framework how to weight different orbital elements. The coefficients will get redistributed back through your preferred values for different orbital elements. So it's tough, but this, we will argue when we submit the paper, is the best method to use to make these maps in the most reliable way. Thank you. Yes.
Of the planet as it moves around. So is this information not helping much in the map?
That's included. So these, yeah, so I glossed over all the details, but these curves are for the full orbital phase, so that we can have as much information as possible. Yeah. But with this analysis, you could actually isolate it, and you can compare how much information you get from the phase curve versus how much information you get just from secondary eclipse by doing separate PCAs and seeing kind of how much your information content of the different components.
Do you know the answer in this example?
In principle, I know the answer, but I don't have the final numbers. Yeah.
Over there?
Yeah.
Yes, Laura.
Secondly, so I'm interested in your branding of the system. Perfect.
Yeah.
Model,
Provocative.
but yeah, it is. I'm provoked. So alternatively, you could argue that there's a lot of additional information that we have based on our physical understanding of the atmospheres, and there are some,
Okay.
and some, so you could have, say, like a kinematic model similar to what, like Nick Cowan developed in 2011, or
Yeah.
Schumann and others, where you have like parcels of gas actually moving around in the atmosphere
Yeah.
in a way that we think we mostly understand.
Well, okay, I'll let you finish your question.
So I guess my question is, you sound very skeptical.
Yeah, as somebody who runs those models, I'm very skeptical.
Okay.
And not,
Observers can believe theory.
yeah, exactly. And not necessarily actually because the models are that bad, but with any model, you're going to have to choose how to set different parameters. And for example, a dirty secret is that the amplitude of our wind speeds, we know, is controlled by how we choose to set our numerical dissipation in the model. And there's no physical basis for how to best choose that. You have to play around with it. So I would rather something that's completely model independent and then try to figure out how the models make sense with that actual observation.
Okay, that's right. And I would say really probably the way we'll go forward with this is we'll still compare.
Sure, yeah.
Last question, Rosanna.
I guess the way you described it at first made it seem as if this is a genuine, detailed degeneracy between the orbital parameters and the surface mapping. And so I'm a little surprised because I don't think you'd be able to break it through a mathematical procedure like that if it really is entirely degenerate.
Yeah, thank you.
Are
Yeah.
you saying that basically there are some general features that seem the same if you don't look at it carefully enough?
No,
And this is a way of separating them out?
So-
Or is it really a full-blown degeneracy and there would be no way of otherwise
Yeah.
saying that?
Thank you. Fantastic question. So I think that finishing this work will help us understand which things actually are degenerate and which things are not. But I do think that there will remain inherent degeneracy because of these symbol cartoons. But what this technique will do is let us actually account and quantify that so that we can say how well we can measure the properties that are degenerate and what they're degenerate with, And if we have things like radial velocity information that can help us constrain some of the orbital parameters, that helps improve our map parameters. And we can maybe make statements like, if you can go out and measure this much better, we'll get this much more mapping information. So I think, I don't think we can magically get rid of degeneracies, but I think we can quantify how much they matter.
That makes sense, because I think if there's a genuine degeneracy that, you know, it really makes things look exactly the same, the mathematics will help you characterize
Exactly.
it, but not to eliminate it.
Exactly, yeah.
Well, we need to move on. Let's thank Emily. Hsin-Yu Chen is a new postdoctoral fellow for our initiative down the road in Garden Street. She will be around for the next 3 years. And feel free to ask her about relations to the library and member of the library. You can ask her any question, but it's not clear that she will answer.
Yeah. Some point I'll stop. Okay, so hi everyone, I'm Hsin-Yu Chen. So yeah, I'm a new fellow down the street, and I'm happy to join the group here. Very excited for all the future interesting discussion. It's gonna take time for us to really say something. It's gonna take some time. So let's talk in a while. And actually, when I was preparing this talk, I was thinking to present a paper I wrote, the latest paper I wrote, but the title is Finding the One Host Galaxy Identification for Gravitational Wave Source. And I found that to be too suggestive, so I decided to change my title. So I figure no matter what happened, it's always interesting to talk about what's going to happen next in the future. So that's mainly what I'm going to focus on today. So just a few slides on motivation. It is a very excited field now, gravitational wave multi-messenger astronomy. We want to capture the signal from source, a signal both in gravitational wave and electromagnetic wave, because they are going to give us independent physical measurement and also measurement of some external parameters. We would like to combine them. There are different ways of combining them, including this electromagnetic counterpart follow-up. I'm also joining this dark energy camera optical counterpart follow-up team led by Guido. So hopefully, if we got the signal from both sides, then we can combine them and get you the full picture of several interesting scientific questions. Here, I just list some major questions people has been talking about. First, it starts with the sender siren, so using the distant measure from gravitational wave side, and redshift measure from EM side. Then we can measure cosmology starting from the expansion rate of the universe. We would like to capture the gamma ray burst and gravitational wave jointly at the same time from the same source, same sky location, if we can localize it that well. Then first, it will resolve this mystery of the progenitor of short GRB. And if we can do it even better, then EM side will measure, we'll follow a light curve, for example, and if we can figure out the jet opening angle from EM side. From gravitational wave side, we have another independent measurement for the binary, which is an inclination angle, and these are thought to be, maybe they should be related, so that will help us to maybe understand the jet structure, or etc. People are also interested in trying to figure out this neutron star equation of states. It's thought to be more difficult because we would need stronger signal to read out those deviation from the gravitational waveform. And also, there's thought to be some information in the EM counterpart. And also, we always like to know about the formation channels. And people talk about this origin of heavy element, possibly come from kilonova, which is a potential EM counterpart of neutron star binaries mergers. All right, so we conclude LIGO first and the second observing round just last just this last month in August, we have released 3.9 solid binary black hole merger detections. And we released about 10 candidates, so some triggers and some candidate events to our EM partners. Another big news is that Virgo joined us just starting this past August and operate for about a month. We'll keep upgrading our sensitivity. Hopefully, we're going to turn the detector back on a year from now. That's what we call the third absorbing run, or O3. And then we have some goal, the design sensitivity. That's the second generation design sensitivity, which is supposed to be at least 2 times more sensitive than the best detector we have now. And 2 times is 2 times further in distance, so you cube that to get the number of detection increment. Okay, so this is also a standard plot we show. This is our noise budget. We are sensitive from about 10 hertz to a few thousand hertz, our sweet spot. So the lowest noise level spot lies around 100 hertz. And recently, just 2 weeks ago, we update this document to give some projection of several interesting parameters that I'm just going to talk about, because I've been helping to put out this number, so transfer this noise curve to the following interesting parameter for everyone. So first of all is the distance, so how far away, and the number of detection we predict. So this is specifically for binary neutron star mergers, the source we are interested in, and plotted in the cumulative number of detection, suppose we observe for 1 year, and as a function of how far away do we see them. So for example, if we look at this solid black curve, that is our second observing round, just the one we just conclude. We expect if you go out, if we expect about 1 detection, order of 1 detections, lying within about 70-80 megaparsec. But actually, you just look at this plot. So that is y-axis is distance, and x-axis is number of detection, which is, if you assume a constant rate, and that's volume. So you would say then luminosity, distance cubed give you the volume. So that's the same information, but actually it's not. So if I really take this is the same plot on the left-hand side. If I really take a log-log plot here, this is not a straight line, which means this is not just x equal to y cube equation. Instead, there's some shape. That means our sensitivity is actually not isotropic. This is not a sphere we are looking at. Our sensitivity is actually, we have some selection effect. It looks like the shape on the right. So imagine LIGO have our interferometer arm to arm L shape. It's like this 2 black line here, like this sticking out. We are more sensitive to sources right above and below our detector, so that we see bigger blob over this direction. We are less sensitive to the direction along our detector plane. So that is not isotropic. This is what we call the antenna pattern. This is something you always want to keep in mind when you try to discuss issues such as a homogeneity of LIGO detection, or if you try to figure out where do we expect more LIGO detection to come from on the sky. This kind of discussion, this is always something you would like to bear in mind. Okay, come back to this plot. For example, now, this endpoint of this 3 curve, by the way, this is O2, O3, and our final goal. So just endpoint in this curve in a vertical direction, that gives you the total number of detection do we expect for this all 3 different stages. If you look at it in the horizontal way, then that tells you what is the furthest source we expect. It goes up. And this is like the furthest is like 200 megaparsec for O2, and then it goes up. And now if you want to use this plot, let's say you try to capture some EM counterpart, you have some EM emission model in mind, and here's your task goal. You try to evaluate your task goal ability to follow up this gravitational wave source. And let's say, from those models, you will say, I can see sources out to 100 megaparsec, then that tells you you will only capture maybe just 1 or 2 detection, binary neutron star, all the way till the end of the LIGO run. However, if you can push it further to, let's say, 300 megaparsec, then that really separate you from other shallower telescope, because that gives you another order magnitude more detections out there. Okay, so that's one piece of information. Another information is always the localization. So still, the 3 stages. Localization, our LIGO localization is mainly based on comparing the arrival time of signal to each detector, to compare that. So when you start to have 3 or more detectors, you will really be able to resolve where the source is on the sky. So now we do have 3. If we improve the detector sensitivity a bit, we will be able to have a better constraint on the arrival time. But what we really want to do is have more detectors. So in the future, we have 5 detector network plan ahead, including not only Hanford Livingston, there's a LIGO-Virgo, there's also LIGO India, and the Japanese detector Kagra. So that's our final goal. And you can clearly see the localization area. Just look at the yellow side, that is localization for binary neutron star merger. It keeps going down. For the binary black hole, which is the blue one, I think it's also interesting. First, this is 10 times larger, which is, and that is mainly because the binary black hole actually spent shorter time in our LIGO sensitive band, emerged earlier. So our timing resolution to them is always not so good. And if you are trying to, for example, capture or constrain the EM counterpart from binary black holes, it's always going to be more difficult than the binary neutron star mergers. Okay, because that's all I want to say. Just hopefully we will capture more swirl on the sky, like in the near future. And I will stop here and take questions.
In a special time and very exciting time in astrophysics. Not very often we have a new messenger that we can probe the universe with. I mean, we've been using photons for centuries, but for the first time now we use artificial intelligence. Questions for Hsin-Yu?
How does the localization depend as you go down that signal to noise curve? So for like the few most distant events that you detect, is the localization similar or worse? Or?
No, it got worse. I just tried to come up, because I actually did a fit in the past, but I forgot the power law. But yes, that's actually something you would always like to consider. So not only if you can capture the EM signal, if that's what you have in mind, also for sources further away, we do the localization worse down the road. So it will be interesting to see a plot like that.
Well, if there are no more questions, I wanted to mention 2 things. One, watch out the news on October 3rd. That's when the Nobel Prize in Physics will be announced. And second, on the 16th of October, there would be a press release by LIGO, perhaps related to some of the things discussed here. Thank you for coming.